Right, let's take what we looked at in the first lecture on molarity and apply it to a little bit more solution chemistry. So in this slideshow, we're going to be looking at the mathematical applications for dilution and molarity. All right, that's what we're going to be looking at here. So molarity, just remember, is moles over liters. It lets us quantify the concentration in a solution for comparison. And concentrated chemicals are common in chemistry. So we usually dilute them down in order to use them, but we store them in concentrated forms. We also purchase them in this concentrated form to avoid shipping issues. So just as a brief example, I have a 18 molar bottle of um, sulfuric acid. Sorry, I lost my train of thought there. And that is probably going to last us 3 years in chemistry. Now, we use sulfuric acid for a lot of different labs. If I had to order the zero point 0.1 molar vials that we use, I would have to order probably, I don't know, 15 or 20 of them. And in the long run, that's hard to store safely, and it's a shipping issue. So it's always easier to just buy these concentrated chemicals, and then we can dilute them down. So that's the premise behind a lot of the questions you're going to see. Like, how do we dilute this down? Now, in order to dilute something, we need to know the dilution equation. And it is M1V1 equals M2V2. You probably remember P1V1 equals P2V2, the exact same idea here. There is an inverse relationship between molarity and volume. So this is obviously very similar to Boyle's law. Now, if we assume that the moles are constant, the molarity of a solution will go up as the volume goes down. This is the graph, right? Pretty simple stuff. Sometimes we write it C1V1 equals C2V2, where C stands for concentration. It means the exact same thing. You can memorize whichever one you want, as long as you know how to use it. Well, why is this useful? Well, if I know the molarity of my stock bottle, right, and I can use the dilution equation, then I can determine how much solvent I need to dilute to get some new concentration. So here's a great example of that, right? I have this stronger concentration on the left. It's a little bit stronger than I need. I need this let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little red dots on the left. And on the right, we have 1, 2, 3, 4, 5. So a little less than half. I need like a 0.45 or whatever concentration. And so I need to figure out how much water to add. And it looks like they added about 75 milliliters there. So they did that using this dilution equation. Now, something to keep in mind, the dilution lowers molarity, right? It's never going to raise it. You can't dilute something to get a stronger concentration. So dilutions always lower the molarity. So let's do a sample problem. It says I need to prepare a total of 25 milliliters of 0.125 molar hydrochloric acid for our next lab. I have 12 molar hydrochloric acid in the acid cabinet. What volume of stock acid should I use to prep the lab? So first, let's look at the problem itself. What are we being asked here? So let's use a pen. Well, the first thing it asks for is what volume? Well, that's not really easy to see, is it? Let's flip over. Can't work again. Let's go black. All right, so we're looking for what volume of stock acid. So we are doing a dilution, so we're going to use M1V1 equals M2V2. And I know that I have 12 molar. I know that I have 0.125 molar. I know that I have a 25 milliliter. I know I'm looking for a volume. So let's plug these in and see what we need to find. Well, my first molarity, the first one I know, is 0.125. And the volume that goes with it is 25 milliliters. My second molarity in the problem is 12 molar, and so I'm looking for my second volume. I need to solve this equation for V2, so that's pretty simple, right? So divide both sides by M2. The M2 cancels out, and I'm left with V2 equals M1V1 over M2. And then just plug in my numbers. Notice milliliters is going to be what's left over, and molarity, molar is going to cancel out. So 0.125 times 25 over 12 gives me a volume of 0.26 milliliters. So what does this mean? Well, this means I go to the acid cabinet. I would use a pipette for this. I get a graduated cylinder that can measure accurately less than 1 milliliter at a time. I get 0.26 milliliters out of the stock bottle that has 12 molar hydrochloric acid in it. I put that down into an empty graduated cylinder, right? I pinch my little pipette and put it in there. And then I had enough water to bring that volume up to a total of 25 milliliters of solution. That solution will be a 0.125 molarity. That's what that number means. Now, there's another tie-in that dilution and molarity brings us to, and that is acid-base chemistry and a titration. Now, next week, we're going to start acids and bases, and we're going to talk about titrations, but I like to use them kind of as a segue between the two topics. So a titration is used to determine the molarity of an unknown acid using bases that we know the molarity of. And obviously, it would also work in reverse, right? An unknown base with a known acid. Now, when we do this experiment, we use an indicator, and an indicator is going to change color based on the pH. Well, if I'm adding acids to bases, I can guarantee that the pH is eventually going to change, right? And we've already talked about types of reactions. We know that the acid-base neutralization reaction occurs when an acid and a base react in order to neutralize each other. So when we do a titration, this is the setup that we are going to see. So we have a Erlenmeyer flask at the bottom here, and suspended over it is a burette. And the burette has a couple different interesting characteristics. Number one, it's kind of like an upside down graduated cylinder. It's very accurate as far as the volume that it measures. And at the bottom, it's got this thing called a stopcock. And you turn it, and there's a little, like a cylinder in here with a hole, or like a channel. And as you turn it, you can very precisely control how much water from the burette or how much solution from the burette travels down into the spout there through the stopcock. So you don't have to open it wide open. You can make it where it's just like one drop every second or one drop every 5 seconds. It's pretty cool, pretty simple little tool. Now, when we want to do a titration, we need to use a titrant, and the titrant goes in the burette. That is the solution that we know the concentration of. In the Erlenmeyer flask, we'll put the analyte. That's the thing we're analyzing. It's the thing that we don't know the concentration of. And to the analyte, we will add an indicator. And the indicator is going to change color based on the pH. So let's say our analyte is an acid, and we add a base to it in the form of a titrant. Then we would want an indicator that's going to change, that's going to be clear when the solution is acidic. It's going to change color as it starts to turn towards the basic end of the spectrum. On another, in the other case, if you have a base and you're trying to titrate that with an acid, you obviously want it to be clear or colorless during, the initial phase, and then to change color as you add that acid. So there are a lot of different indicators that we use. And when we do a titration, we generate this curve. And the curve is pretty simple, all right? The curve has the pH on the y-axis, and obviously the pH goes from 0 to 14, all right, 0 to 14. And on the x-axis is the volume of our titrant that we're adding. So in the first curve, we're adding a base to an unknown acid. In the second curve, we're adding an acid to an unknown base. Now, you should be able to spot that immediately, all right, by looking at this. And that is because wherever we start, which is always going to be on the left, right, when we haven't added any volume, the pH down here is really low. So the low pH tells me that the equals titrant is an acid. And if we start with a really high pH, this means the titrant is a base, right? It's starting out as a very strong pH. Now, when you look at this thing, this curve, at first, the slope is very shallow. So there's a very little change, a very slow change to the pH as we start adding base. Now, when you get near what's called the equivalence point, the pH change becomes very rapid. We have a very steep slope. So if we look right here at the tangent line to the curve, let's say we'll pick 3 different points. Well, at this point, the slope of this line that's tangent would be pretty smooth, pretty low. Here it's steeper, so obviously there's greater change per unit time. And on this one, it's almost vertical. And at the titration point, it's literally almost vertical. So we have a change in the rate of our reaction here. Now, once you pass the equivalence point, the rate of change is going to slow down again. So if we look at, well, technically we should have drawn it like this, right? Our initial rate there, our second one, our third one, right? Now, once we pass the point of the equivalence point, which is what this dotted line is showing, I'm going to have another steep, another slow, and it's going to keep slowing down. Now, the equivalence point is very important. It's the point where the moles of the acid equal the moles of the base in solution. And why do I know that? Well, remember, molarity is moles over liters. So if I know the point where the moles of the two are equal, I can figure out the starting molarity of my unknown, right? Because I know how many moles there are, and I know how many liters I started with, and moles over liters is my answer. Now again, remember that low pH at the start means you have an unknown acid. A high pH at the start would mean you have an unknown base. And there are 4 steps to these. So we need to write and balance a chemical equation. It's going to be a neutralization reaction. So you know you're going to have an acid reacting with a base, and it's going to make water and some kind of salt, a metal and a nonmetal salt. We need to identify the number of moles in the titrant. That's sometimes also called our standard solution. We need to use mole ratios to solve for the moles of the unknown, which I'll show you how to do. And then we, obviously, once we know that, we solve for the unknown. The unknown might be a molarity or it might be a volume. We can find either one. So let's look at this problem. This is how many milliliters of 0.45 molar hydrochloric acid must be added to 25 milliliters of 1 molar potassium hydroxide to make a neutral solution. All right, well, first let's write and balance our equation. We know how to do this. We know we have hydrochloric acid. It's going to react with KOH to produce water and a salt. The salt is the metal and the non-metal coming together. We know K is +1. We know Cl is -1. So when we do the cross-charge method, we end up with KCl. We would need to balance it. So we have a chlorine on both sides. We have potassium on both sides. And we have HOH, HOH. So everything is good. We have all ones there. Now, the second thing we need to do is identify the number of moles in the titrant. Well, it tells us, all right, that our known solution is KOH. It tells us the molarity. And so moles over liters is our molarity equation. We can solve that for moles. So molarity times liters. And we say 1 molar times 0.025 liters, which is what we have in the problem, right? 25 milliliters. 25 milliliters divided by 1,000 milliliters in a liter, right? Okay, that's how we got that number. Gives us 0.025 moles of KOH. Now, we can use the mole ratio of KOH right here to HCl, to our acid, the mole ratio, to solve for the unknown. Now, in this case, it's 1 to 1. So if we have 0.025 moles of KOH, then we're going to need 0.025 moles of HCl. It's a 1 to 1 ratio. Now, be careful. That's not always true. If you have a 2 as a coefficient, it might be 1 to 2. You'd have to double 1. Or maybe it's 2 to 1, or 2 to 1, you double it. 1 to 2, you'd have to half it, right? So just pay attention to our molar ratio. Now that we know our moles, we can solve for the unknown. So molarity is moles over liters. The question asks how many milliliters, so the volume. So we solve for liters, because remember, this liters, that's a volume. So liters equals moles divided by molarity. We have 0.025 moles of HCl that we figured out. We have 0.45 molar HCl from the problem. Volume is 0.056 liters. And we need to convert to milliliters because, we got to read the problem. It says how many milliliters. So RTP means read the problem. And there we go, 56 milliliters. So titrations are not all that difficult. They're pretty easy. They take practice, obviously. We'll look at some more of these when we get to the acid and base section, but it's a great place to start. So now that you know how to do this, I know there are a couple in your book we can try this week, so give them a shot. And if you have any questions, let me know. I'll be glad to give you a hand. All right, I'm here to help. But other than that, I will see you guys in the next video.